In order to understand the acceleration, we need to understand the convergence of the unaccelerated method. So we will first look at the convergence of gradient descent on P. So this is a problem P. Here we consider a simple version that is without the constraint. If there is a constraint, the whole theorem stays the same. You just need to tune somewhere for a little bit, but the idea keeps the same. Since P is a quadratic function, so you can have a convergence rate that is more precise than a general F. So the theorem is like this. You have a step size T. If the step size fulfills this thing, then the convergence is guaranteed. So what is this thing? So this lambda max is basically the full norm of the Q. Then that means what? That means this thing, absolute value, smaller than 1. That means T cannot be too big. If T is 99999, then basically you can take this one is 0, then you are taking absolute value of a 99999 multiply something, then definitely won't smaller than 1 if this is larger than 1. So that means basically it means T cannot be too big. And this is the same, but you just change the lambda max to lambda min. So basically it means step size cannot be too big. So this is the theorem. Why this is true? Well, I will say this is a reading exercise. So I'm not going to talk about each line. So basically, you have the F here. So you have the gradient. So the gradient design is looks like this. So you plug in the gradient, factorize them, and then eventually you will get this form. And remember, first order optimality condition. That means when the point x star converge, that means the solution gradient is 0. So you get this. So you plug in this line with this x star, and then you subtract this thing by x star, and then just a bunch of algebra. You have this inequality. For this to converge, you want this guy to be smaller than 1. How to make sure that's smaller than 1? Basically is this thing. So Q is bounded by this thing. I consider L is largest lambda of Q, and then this is mu is the smallest lambda of Q. So you have this. This is the semi-definite inequality notation. Then you, after a bunch of manipulation, you will have this for the T at Tk. That means step size at Tk. But since you are using constant step size, so you can treat them all the same. But here is the theorem. So this is just the idea on how to read this slide. So you can read it in your spare time. In order for the gradient descent to converge, you need to fulfill this thing. So this is basically Tk is not constant, so you have to multiply every term. But let's say they are constant, then all these terms are the same. So this multiplication become power. So because this is a max of these two things, so you have two cases, either this is bigger or this is bigger, but they are the same. So let's consider the first case. You want convergence, so you want this number to be smaller than 1. So this is smaller than 1, this is absolute value, then blah, 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 then you will get this thing. So basically it means T has to be smaller than 2 over L. And it's the same for the mu. So here is the convergence theory. For this problem T, you want to minimize it, you want to pick the step size as 2 over L. Now you remember for gradient descent, previously I told you for the constant step size, you will take T as 1 over L. 1 over L is smaller than 2 over L. So why would people pick 1 over L? It's because of this theorem. Here is the illustration. So if T is 1 over L, then you plug in this thing, T is 1 over L, then this T becomes 1 over L, this is 0, right? And this max, so this 0 goes away, and you have this thing. And you have a K power here, so you have this thing. And this kappa is basically the L over mu. So now you have inverse of kappa. We call that L is the largest eigenvalue of Q, and mu is the smallest. So of course, the largest eigenvalue will always be larger than the smallest eigenvalue, unless they are all 1, then this is always larger than 1. Well, if they are all 1, basically it means this Q is identity matrix. In this case, the objective function reduced to the circular case. This is 1, so this is 0, and this is 1. Then 1 minus 1 is 0, so you go to solution in 1 step. So gradient converge in 1 step. But if kappa is 999, so basically you are multiplying this with 0.999 something. That means the distance between the new point to the solution is just 0.999 something of the distance between the old point to the solution. So basically it means it does not move much. So that's why slow convergence. So this is the meaning of this theorem. What about the base T, that is 2 over L plus U? You have this thing. Well, basically I do it here, you read later. So now here's the thing, you see something. If kappa is 1, that means the level set is circular. Then this is 2 over 1 plus 1. This is 1. 1 minus 1 is 0. So again, gradient descent converge in one step. Again, if kappa is 9, then same thing, converge very slow. And if we compare this step size with the 1 over L, so let's say kappa is 2, actually we get 1 over 2k for the 1 over L versus 1 over 3k for the base T. So that means this is slightly faster than the 1 over L. But to use this one, you need more information. You need to know this one. So this is the summary. You want to solve the P, and then you use gradient descent. And this is the convergence. As long as your T satisfies this condition, then the sequence will converge to the minimizer. And with different step size, you have different rate. And this is slightly better than this one. So I have just talked about the convergence on problem P. Now let's talk about the convergence on general F as long as it's L smooth. This is a theorem. If this is true, then you have this. Or in other words, they are equivalent. Actually, if you have this, you can show from this, you have this. Or you have this, you can show this, you give you this. They are the same thing. So how to show it as a reading exercise, you just read the proof in these 2 slides. A function is L smooth means that this function is bounded above by a quadratic function. Because this blue thing is on top of it, this green thing cannot go above the blue thing. That means this green thing cannot grow too fast. F cannot grow too fast. Cannot grow too fast means the slope of this green thing cannot be infinitely big. Because if the slope is very big, that means this F have to grow very fast. That will over this blue curve. So this is the message. That means if F is L smooth, then it cannot grow too big. Then it will bound above by something which is a quadratic function. So this is the meaning. Now another inequality is called, I don't even know how to pronounce this name. This is a Polish name. Polyak is the Polyak's heavy ball method. That's the one I showed you before. So what is it? Basically, it says that you have function f. If it is differentiable, then the norm of the gradient is bounded by this thing. So why I suddenly introduce inequality that I don't even know how to pronounce the name? Because this is useful. That's it. Something I skip, which is impossible to discuss in a 2-hour lecture. That is, this is true for many functions. In fact, it's true for almost all semi-algebraic function, blah, blah, blah. There's lots of terminology, but basically it means that for the task you do, let's say machine learning or data fitting or clustering, the function f you use basically will satisfy this inequality. So you can assume this is true for your program. So how to prove convergence of GD? First of all, the function f is L shift. So that's why you have this inequality. This thing you can put into this thing. Why? Because this holds true for whatever x and y. So you can let the y is xk plus 1 and x as xk. You can do that. So this term is a minus term become this term because xk plus 1 minus xk is negative 1 over L gradient thing. So you can plug in here, and this is the same. So that's why after algebra you will get this term. This equation actually has a name called descent lemma. This actually is the important lemma. What does it mean? It means when you do gradient update, well, using the shift step size, then the function value will decrease at least this amount. So this is called the descent lemma. This quantifies how much gradient descent goes down the f for one step. So this is the important lemma. So what is the message here? You have the L shift, you plug in the gradient update, you get this descent lemma. Then what's next? You use the PL inequality. So PL inequality is like this. So this thing is smaller than this thing, so the whole thing can be bounded by this thing. So you get this term. And then now for this thing, you subtract both sides by f star, and then you just do algebra, factorize it, then you will get this thing. This is at iteration k. Then this is the same for k minus 1 and k minus 2, blah, blah, blah. So finally, you have this k in the power because you use constant step size. So this is convergent. This is something similar to what you see before. So basically, this is 1 minus 1 over kappa. This is 1 over kappa, because kappa is L over mu. So this is the same thing, but now this theorem is for general F. In the whole proof, actually, I didn't use the fact that F is convex. So basically, this convergence proof works also for F that is non-convex. And what about the proof also applies. So now move to APG. And as I show you, the proof is quite hardcore. And in fact, the proof of Nesterov accelerated gradient descent in the original form in 1983 is even much more hardcore. That is almost unreadable. We will look at the convergence in another way. So first of all, talk about the convergence rate. So this is the definition, and this value will give you the convergence rate. If this value is 1, it's called sublinear convergence rate, which looks like this. And if this value is 0 and 1 inside, it's linear, so it's a 9. And if this is 0, it's called superlinear, which is faster than linear. That means a line looks like this. And here, the definition is using F. It's possible to use this or this as the convergence definition, but it's the same. So as I show you, this is called sublinear. This is called linear. So you see, this is a straight line, almost a straight line. So this is linear. This is not linear because at the beginning is a curve. So this is sublinear. And if you express the convergence rate in terms of the number of iteration, k, gradient descent will converge in this fashion, and accelerated gradient descent will converge in this fashion. And here's the amazing fact. This is actually the optimal rate. That means you can never run faster than accelerated gradient. Let's talk about convergence rate for problem P. Now for accelerated gradient, this kappa becomes square root kappa. So this is the only changes. So let's assume, let's say kappa is 2. Then actually we will have this thing is 1 over 3. And this thing is 0.17 something. So basically the convergence is this versus that. So for 4 iteration, you will see the difference. The number is like this. For the 4th iteration, this number is already 100 times better, smaller than this number, 2 digits smaller. So you can see if you run this more iteration, it goes down much faster. Now we want to study this. So let's go back to the problem P. And to study this, we will make the problem easier. That is, we assume this is 0. If we assume this is 0, then this is 0. So we only have this thing. So the optimal solution is very simple. You want to minimize this. So what is the best x? Well, just 0. Given a symmetric positive definite Q and find the x such that admin this, of course, we know x will be 0. But let's see what happens in the Nesterov gradient. So this is the Nesterov gradient. This is gradient step. This is the extrapolation step. First, this is Nesterov gradient in one line. I can further simplify into this line. Here is eigen decomposition. So eigen decomposition on Q, this bracket becomes this thing. I multiply the whole equation on the left by V transpose. V transpose with the V cancel out because they are orthonormal. And here the same, V transpose with this V cancel out, so gone. So I have this thing. Now this thing, I can factorize the V transpose out here, multiply into this bracket, so I have this thing. So now I have this with this, and now I rename V transpose X as W. This is at iteration K plus 1, so I have W at K plus 1. This is iteration at K, so I have WK, and this is length, so I get this expression. So what is the meaning from here to here? It's basically, I express the Nesterov gradient descent in one line, and then I plug in the gradient, and then I factorize them, and then I do an eigen decomposition. The meaning of the eigen decomposition is actually to rotate the X such that they decouple, because I have this equation, and since this is a diagonal matrix, so it looks like this, and this is also a diagonal matrix, it's just 1. So basically it means the first component is equal to 1 minus 1 over L times lambda 1, and multiply this times the first component and add this times the first component. The first component is independent to the other component. So basically I decouple them into this elementarized expression. So that means this V transpose is actually to rotate this X to a new coordinate such that all the components are decoupled. Because previously here, this Q is not a diagonal matrix. That means the first component will be linked by some other component. But after doing this, I decouple them. Then I have a scalar equation. So this means the ith component of W at the iteration k plus 1 is only a constant multiplied by this expression. And remember, this beta is the extrapolation rate. So if beta is 0, then we go back to gradient descent. And this also works for gradient descent. So now we can study the convergence on studying this equation. So what is this equation? An equation that describes dynamical system. You have to study it using characteristic equation. So this is actually like discretizing an ODE. So you have the characteristic equation, which looks like this. This is a quadratic equation. So you can solve this on beta. So this is like the best beta you can have for this equation. What is the best beta for this equation mean? Means the beta makes this go down to 0 as fast as you can. So what does it mean? This characteristic equation is actually modeling a second order ODE, and this is obtained like by discretizing a second order ODE. So for different beta, there are some meaning. For the best beta, which I shown here, that is described like this. This best beta means that you have the best amount of momentum in the gradient update. And because you add the best amount of beta, the convergence should be the fastest, of course. And this physically described as the system is critically damped. That means the momentum is actually act as something like mechanical friction. This is the figure. If you have a critically damped, this curve will go down like this fastest. If you have something called over damped, then you will have this thing decrease slow, much slower than critical damped. And lastly, for under damped, then you have this kind of behavior. Then this never stabilizes because theoretically speaking, it takes infinite number of time for this to converge. So this is even worse. So this is the explanation in terms of a dynamical system. The acceleration of the Nesterov method actually comes from something like damping. So this is a partial explanation. That means this is not a full explanation why Nesterov method is fast. This is just a partial explanation. Because why Nesterov method make it fast is still a mystery. And lastly, this picture, this slide saying that this kind of ripple is periodic. Because this is like a second order ODE, then you can solve for the solution point. For second order ODE, the solution point will be cosine and sine. That's why you see the sine cosine thing, and this is just constant. And for the sine cosine thing, you just match the parameter K5 with this alpha beta, then you will get this crazy expression. And then you will see that actually the 5 is approximately equal to inverse of the kappa. Basically, that means how big is this ripple is approximately related to this value, which is the kappa. What's the kappa? Is the L over mu, that number. But this is inverse. Well, I'm not going to show it because it's too involved. If you have free time, you can try to derive it yourself. So this is a damping explanation of why acceleration works. And then lastly, we will look at it using ODE. As I showed you, this is like a discretization of a second order ODE. Then why don't we look at ODE directly? So now from Nesterov acceleration, now we use a very simple Poisson's parameter. That is, the beta looks like this. We don't use those crazy alpha beta rule. We use this because this is simple. The Nesterov accelerator have convergence like this. I'm going to show you this thing and this thing are related. And notice that this beta is not the one proposed by Nesterov in 1983, because the 1983 method is a bunch of alpha beta with crazy formula. But why we choose this is just because this is simple. That's it. Because if you pick the alpha beta with the formula, then the ODE becomes very ugly. So how to derive the ODE? So basically, this is a Nesterov gradient descent. This is yk plus 1 equal to xk plus 1 plus the momentum term. This is yk, so you want this to be yk, so you get this. Put into this y, then you will get this line. And then move this k here, then you have this line. So this is the starting point. So why do this? Number one, we cancel the yk. We have two equations. We don't want two equations. We want one, easier to deal with. Number two, we get finite difference term. That is, we get the thing that looks like this. And then you divide the whole equation by square root t. So you have this, I label as 1. The goal is to derive ODE from 1. Why divide it by square root t? It's just because it will cancel some term. It's possible you don't divide it by square root t, you can still do the same thing. So we now want to derive ODE from this thing, because this is a discrete equation. So that means we need to link discrete iteration with time. So let's say we do this. Because we divide it by square root t, so let's say we divide like this. Iteration at k, this is discrete iteration, is equal to tau divided by square root t. Tau is continuous time, square root t is step size. And because of that, this thing now approximately is equal to this thing. Then we need to use Taylor series. Now we have this thing and we have this thing. We can plug into 1 to replace this term and this term by the ODE thing. Then we will get this thing. So this is the idea. Once you get this thing, what you do next, of course, you rearrange them and group similar term. So you have this thing, you rearrange. So now you have this thing, but you still have the y. Basically just y is x. So you have this. Now we hide this notation. So now we have this ODE. So now we want to plug in the beta and also want to remove this guy. So now we choose beta equal k over k plus 3. Because here we want beta k minus 1. So beta k minus 1 become this fraction. So now you get this ODE. And now you see there's square root t, square root t, square root t. So you divide the whole thing by square root t. And now you take limit t equal to 0. So you have this ODE.